Welcome to the office. We want to take a look at some examples. The first example that we're going to take a look at actually does use the idea of a homomorphism to try and develop our understanding of the quotient groups. So we're going to consider something that might be relatively comfortable to us, or hopefully is comfortable to us. And we're going to consider a collection of questions to kind of develop this idea of our quotient group. And then we'll take a look at some other examples that are a little bit more brief, where we just consider the idea of a normal subgroup rather than the kernel of a homomorphism. So let's see here. We want to consider the factor group Z mod 12Z, or quotient group. That's right, quotient group or factor group, that's fine. And then we could read this as Z mod 12Z, and that's good. Now, the reason that we call it Z mod 12Z is actually going to make a lot of sense after we talk about this example. So what homomorphism does this factor group result from? All right, so what I want to do is I want to find a homomorphism phi whose kernel is exactly 12Z. So let's define phi, a mapping from Z to Z12. Mapping from Z to Z12, defined by phi of n is equal to R sub n, where R sub n is the remainder obtained in the division algorithm when n is divided by 12. All right, so phi mapping from Z to Z12 defined by this. All right, so what we get here, we've already taken a look at this homomorphism actually, but all of our possible remainders are the numbers 0 through 11, which is exactly Z12, of course, but then we're going to get that this is equal to 0 at every multiple of 12. Oh, hey, look, that's what 12Z is, every multiple of 12. All right. So what homomorphism does this factor group result from? We have answered that question. Is it necessary for us to make this observation to conclude that 12Z is normal and that Z mod 12Z is a quotient group? Well, no, it's not actually necessary. So it's nice if we can observe that a set like 12Z is a kernel of a homomorphism, then we know that it is normal. And that's wonderful, because then we can take Z mod 12Z or G mod H, whatever it happens to be, and conclude that it does form a group, a quotient group. However, in this case, since we actually have the really basic piece of information that Z is abelian, right? It has that commutative property for its operation. So the group itself is said to be abelian. Since we have an abelian group, we automatically get that left and right cosets are the same, and therefore we have that every subgroup of Z is actually a normal subgroup. Every subgroup is normal. So we don't need it in this case. However, it is a little nice just to get that big picture understanding, or I guess as we dive into the details, even what have we got going on? Kernel. Okay, yes, fantastic. Excellent. So what does the previous theorem now, so developing a little bit further, what does the previous theorem tell us about the structure of Z mod 12Z? So we have to refer back to our previous theorem. So there was something useful in here. Yes, awesome, right? That new piece of information was the map mu. The map mu is a mapping from G mod H to phi of G, and it's saying that it's an isomorphism. It is an isomorphism. That means I'm saying that these two groups are the same thing. So when I look at our group right now, well, under this homomorphism, phi of G is exactly Z12. So what we're saying, what does the previous theorem tell us about the structure? Well, what it tells us is that phi, or what we can observe, so we observe that phi of G is exactly Z12 because, of course, we are familiar or comfortable with the idea that phi is at least onto. It's certainly not one-to-one, but it's onto, which means that phi of G is equal to that. So by the previous theorem, we actually get that Z mod 12Z is isomorphic to Z12. So that tells us exactly what the structure of Z mod 12Z is. It has the same structure as Z12. Boom! Easy peasy lemon squeezy, right? This is good. All right. What is the order of the group, right? So what group are we talking about? We're talking about G mod H. So we're talking about Z mod 12Z in this case. So what is the order of the group? Now, in this case, what we have is the order of Z mod 12Z must be the same as the order of Z12 because they're isomorphic, which means that it just has the 12 elements. But could we have identified this without knowing the structure of the group? And that's a little bit more difficult to answer. If I didn't know that it was isomorphic to Z12, would I have known that it had exactly 12 elements in it? Well, yes. I mean, I suppose, right? This tells me more than just how many elements are in it, right? Knowing the structure. This tells me that it's commutative, that it is cyclic, that or that it's abelian rather, and that it's cyclic. It has all these nice properties, but that I don't need to know those. I just need to know how many. And I could have observed it from here in uh, my definition of V to see that the equivalence classes, that is the cosets, are exactly the distinct remainders. Well, there's 12 distinct remainders, 0 through 11. So I could have been able to respond to this question, but you got to think much more about the context of the problem, right? What are the specific groups? What's a group and a subgroup there to be able to develop that idea? It will turn out to be a little bit easier yet as we move into finite groups, because again, what is Z mod 12Z? Well, 12Z is exactly the normal subgroup, and this whole thing is exactly the collection of cosets. And we know a relationship between the size for a finite group. We know the relationship between the size of the group, the number of cosets, and the size of the subgroup, right? We know the subgroup divides the size of the group itself, and that other factor that's lying in there, right? Size of G is this times the size of its subgroup. That other thing is exactly the number of cosets. So when we have that G is finite, that is a finite group, then we can actually get that nice relationship according to essentially Lagrange's theorem. Lagrange doesn't actually specify all of it, but in that discussion leading up to Lagrange's theorem, we can get that relationship between the size of the group, the number of cosets, and the size of the subgroup. So that makes life a little bit easier for us. And again, in the case of a finite group. Well, that'll be a part of our next example. So let's now give, still contained in the same example, let's give an example of addition in the group, then consider another example which utilizes different representatives for that. So let's take a brief look at that. So since the operation is addition in Z, that's what we're looking at. And we want to use H is 12Z, right? We're looking at G mod H is Z mod 12Z under addition. So since it's addition and we're using H is this, we get cosets written in the form A plus 12H. Sorry, 12z. So it's multiplication is not the operation here, addition is, and so we're using addition as that operation because that's our operation. No surprise there. So what I could do is I could take something like 3 plus 12z, right? That's an element in z mod 12z. And then I could add to that 5 plus 12z. And according to our definition for coset multiplication, right, multiplication is the generic term for whatever the binary operation is. In this case, addition. So that's going to give us 3 plus 5 plus 12z. And of course, this is perfectly convenient to write as 8 plus 12z. There's no big deal there. But what I could do is I could look at different representations for 3 or 5, or just take a look at some different things that extend beyond. So for example, 7 plus 12z plus 8 plus 12z. Right? Both of these are convenient because 7 is between 0 and 11 inclusive. So this is what I would expect to see as I work with elements. However, what that's going to give me is 7 plus 8 plus 12z. 7 plus 8 is 15. And that just feels a little bit weird. 15 plus 12z. Because 15 doesn't lie between 0 and 11 inclusive. So I would say, all right, well, 15 mod 12 is 3. So this is 3 plus 12z. Right? I can take any, I can add or subtract any multiple of 12 to this, and I end up with the same equivalence class. Okay, they have the same remainder. So pretty straightforward there. Very convenient. Very convenient. All right. So we want to give the order of the element 3 plus 12z in the group. Excellent. Excellent. So how do we approach this problem? Well, the order of an element is the order of the subgroup generated by that element. That's fine. You can think of it that way. So look at all the elements that are generated. Or we can think of it as the smallest multiple that's going to give us the identity. Again, I say multiple in this case because we're working with addition as our operation, not multiplication as our operation. If it were multiplication, then I would say the least power that I can raise that element to get the identity element. Okay, so let's see here. Make a few observations. Maybe not all of these are necessary, but just to make sure we're familiar with what's going on. The identity element here, okay, the identity element in z is 0, so we can call it 0 plus 12z, or simply 12z. That would be fine. But the reality is that we can take any multiple of 12, so n times 12 plus z. All of these would be considered identity elements, any multiple of 12 plus 12z. There we go. I also want to notice that n times a plus 12z, right? We haven't really talked about notation here, at least not a lot. So when we have addition is our operation, repeated addition is represented by multiplication. So a plus 12z plus a plus 12z plus a plus 12z, right? Repeated, if I do it 3 times or 3 terms, then I would have 3 times that quantity. Repeated addition. I can observe this as n times a plus 12z. Again, I could expand that out through the use of the repeated addition, and then recognize that that's a plus a plus a plus a n times, and that's just na, right? That's what we're interested in there. So let's see here. Oh, that's not that equal to something. So we're looking for what we're looking for is this thing and that thing to be equal. So I need to compare these in some way. So I'm looking for NA to be, so I've used maybe bad notation here. maybe I should have used a k here, because this n and that n certainly would not match unless a were specifically 12. So if I use a k here, then I'm looking for na to be equal to k times 12 for some n and k that are integers. But I'm looking for the smallest such n, right? So if I'm looking for the smallest such n, I want to recognize that what I'm looking for is I'm looking for a least common multiple, right? If I consider the least common multiple of a and 12, oh, I have a specific value that I'm using for a here, a plus 12z. So I'm looking for n times 3 to be equal to k times 12. So I have least common multiple of 3 and 12 is 12. That's the smallest way that I can make these two things equal to one another. So I'm going to choose k equal to 1, and that's going to give me n times 3 is equal to exactly 12. And now I can find my value for n. So, all right, let's see here. That gives me n is equal to 4. Boom. Easy enough. The order of 3 plus 12z is 4. That's the smallest number that I can take that many terms of 3 plus 12z. 3 plus 12z plus 3 plus 12z plus 3 plus 12z plus 3 plus 12z is 12 plus 12z. Well, that's precisely um, 0 plus 12z, or the identity element. So that's what I was looking for. All right, so kind of in our discussion that we just had, we had the idea of this quotient group, and we used remainder theorem to help us out there. So we're talking about addition modulo 12. So kind of bringing that into this idea of what we've done. Hey, we've taken our entire, right, we have our group is isomorphic to Z12. This is addition modulo 12. So this quotient is the same as modulo. So Z mod 12Z is the integers mod 12. Right? That's what we're looking at there. So that's why we call the quotient group, or the factor group, G mod H. Excellent. Let's take a look at some additional examples. These additional examples won't require us to discuss mappings. They'll simply have us work through finding the order of a group, finding the order of an element, trying to make sure that we have that idea solidified. So if you didn't like that last example or last bit of that example, we'll take a look at some more of those in our upcoming videos.